of all three tails. These measurements reveal the velocity of molecules and particles moving away from the comet. Natural dust driven by sublimation typically moves at hundreds of meters per second. Anything in the kilometers per second range requires special explanation and more sophisticated physical models. Avi Loeb pointed out that spectroscopy will provide the clearest answer about the nature of these structures. If velocities correspond to known natural processes, then even the sharp anti-tail can be explained within traditional cometary physics. But if velocities exceed expected values for natural degassing, then scientists will need to seriously reevaluate their theoretical models. This is why, hey everyone, today we're analyzing one of the most surprising discoveries in the ongoing history of the interstellar comet known as 3I Atlas. This object has repeatedly defied expectations, but the most recent observations add a completely new layer to the puzzle that has intrigued the scientific community. A new image captured in Thailand shows something astronomers didn't expect at this stage of the comet's journey: a sharp and persistent anti-tail pointing almost directly toward the sun, and simultaneously two separate tails pointing away from the sun. For many observers, this was genuinely shocking. At this point in the orbit, cometary dynamics. A comet typically produces one or two main tails. The first is the ion tail, made of charged particles pushed away from the sun by solar wind. This tail is usually straight and bluish. The second is the dust tail, which forms from small particles gently pushed away from the sun by solar light pressure. These particles follow curved trajectories, creating a broader and smoother tail. The anti-tail is a special case that deserves detailed attention. It's not actually a physical tail pointing toward the sun. Instead, it's an optical effect that occurs when large particles, often debris the size of pebbles or gravel, remain very close to the orbital plane and reflect sunlight in a specific way. When Earth crosses the comet's orbital plane, the geometry makes it a natural anti-tail should have disappeared, weakened, or dispersed into a broader structure. Instead, this anti-tail is clean, structured, and sharply defined, and alongside it, two distinct tails extend outward, each with its own shape and texture. All three structures appear simultaneously, forming a highly unusual configuration that is making scientists rethink their theories. This development comes just as Harvard astrophysicist Avi Loeb shares new comments in his Medium article titled "The Ongoing Saga of Anti-Tails and Tails Around 3-1 Atlas." His analysis helps clarify what we're seeing and why it matters so much for our understanding of cometary physics. These new images once again highlight that 3I Atlas behaves differently from most comets we've seen before. To understand what makes this configuration so unusual, we need to start with the fundamentals of pushed away. This could explain temporary sharpness, but it's unusual for such fragments to persist and maintain coherent structure long after perihelion. The third possibility is more complex and intriguing. It suggests that the structures may be shaped by directed jets that behave in a more organized and stable manner than typical natural degassing. This doesn't assume any predictable streams. However, experienced observers note that the pattern of the anti-tail combined with the two outward-pointing tails resembles a controlled or stabilized configuration rather than a chaotic one. This doesn't prove anything definitive, but raises interesting scientific questions about the physical processes involved. Now, let's put these new observations in the context of previous anomalies we've already documented. 3. I appear that a tail is pointing backward or toward the sun. This effect usually appears briefly, peaks, and then gradually disappears as particles disperse. But in the case of 3-1 Atlas, the anti-tail isn't disappearing as expected. It's becoming sharper and more persistent, and this makes scientists question what type of particles are within it and how they're being ejected from the nucleus. Now let's talk about why the anti-tail's persistence is so surprising for current scientific models. In a normal comet, large particles in the anti-tail naturally spread out, decelerate relative to the nucleus, and eventually disperse into space. The structure smooths out over time due to gravitational forces and solar radiation pressure. But in this new image from Thailand, the anti-tail remains sharp and narrow, maintaining its structural definition remarkably. This can only happen under very specific push them away quickly. They remain in the orbital plane for extended periods and form a sharp anti-tail. The problem with this explanation is that the volume of particles needed to maintain such a sharp anti-tail at this stage would be extraordinarily large. The second possibility is that the anti-tail is formed by icy fragments that break away from the nucleus before sunlight can accelerate them significantly. If these fragments are large enough, they act like temporary mini-comets, reflecting light strongly before eventually being. Atlas has already shown a sun-facing jet lock jets that don't rotate with the nucleus, measurable non-gravitational acceleration, and a surprisingly robust nucleus that survived perihelion without significant fragmentation. It also exhibited an expanding ion tail that remained active long after solar heating began to decline. Each of these observations alone can be explained within the parameters of known cometary physics, but together they form a pattern that requires careful study and possibly revision of some theoretical models. Let's now explore the details of the Thailand image more carefully. The image shows by surprise is that the anti-tail is almost identical in sharpness to previous images taken before perihelion. Normally, perihelion is the moment when a comet releases its strongest and most intense degassing. After this point, tail structures usually calm down and become less defined, but 3I Atlas isn't following this expected pattern. In fact, the anti-tail appears as active and structured as it was before the perihelion passage. This leads us to the key scientific question: why is 3I Atlas's anti-tail still so strong and well-defined? The answer may be related to the internal composition of this unique interstellar object. If 3I Atlas contains a mixture of ices and materials not commonly found in comets from our solar system, it may release particles in unusual and prolonged ways. For example, carbon monoxide and molecular nitrogen ices can sublimate at lower temperatures than traditional water ice. If the nucleus is rich in such volatile materials, it could continue releasing large particles even after pacific conditions. If very large particles are being continuously released, or if the release mechanism is more focused and directed than usual. Large particles would require extremely powerful degassing from the deep interior of the nucleus. On the other hand, a directed release, almost like a controlled jet, could concentrate particles into a well-defined stream. This leads to the three main possibilities scientists are seriously considering now. The first possibility is that massive dust grains are being released in large quantities. These grains, which may be millimeters in size or larger, are heavy enough that solar light pressure doesn't close to the sun and beginning to move away. This is consistent with previous spectroscopic readings that detected carbon-based molecules in the coma. These molecules may indicate that Atlas formed in an extremely cold region of its natal stellar system, possibly at the distant edge of a protoplanetary disk where exotic materials could condense. Now, let's consider the role of observational geometry. An anti-tail only appears sharp when the line of sight aligns properly with the orbital plane. Observers in Thailand had a tail structure. This configuration must come from actual physical outflows. Let's now explore what astronomers will study next. The main goal is to obtain detailed spectroscopic measurements. The next month is so important for research. As the comet approaches its closest point to Earth on December 19th, astronomers will have the best chance to measure the detailed dynamics of each tail. The anti-tail, dust tail, and ion tail will respond differently to sunlight and solar wind as conditions change. Observing these changes over time will show which structures are stable and which are temporary, providing crucial insights into the underlying physical processes. Now, let's talk about observation timing. Atlas is now about a month from its closest approach and remains remarkably active. During this critical